to Tuesday's edition of Cracking the Cryptic, where I want to start today's video by saying a very happy birthday to Anne Mahoney. And I think Anne Mahoney goes under the pseudonym Prof Meow over on Discord. And I hope I've got the day right. Your sister Sally told me it was your birthday today, and I hope you have a super day filled with lots of cake. Now, what have we got for you Sudoku wise today? Well, we have a puzzle called Disarray. Now, this is by two authors. It's by Full Deck and Missing a Few Cards. And I happen to know two things about Missing a Few Cards. Firstly, Missing a Few Cards is a pseudonym of a famous mathematician. And secondly, it is that famous mathematician's birthday today. So we're doing this puzzle on his birthday, and that seems a very appropriate thing indeed. Happy birthday. Now, I'm not sure if I'm allowed to reveal the name of, or the real name of Missing a Few Cards. I'm going to be a bit naughty, I think, and hint at it. Have you heard of the Tree of All Fractions? Well, some of you mathematicians out there will have done, and that might be all the hint you need. So anyway, I hope I'm not giving away too much there. But this is, this should be a special puzzle. Apparently it is quite approachable today, so we ought to be in for a treat. Now, do I have anything else to tell you? I should tell you as well that Full Deck is also a very, very good mathematician as well. So the channel does seem to be watched by an incredible number of very, very clever people. I got an email the other day from a professor at my old university, a professor of mathematical biology. So, you know, we have all of these incredible viewers. We are very blessed, it is true. Anyway, I don't have any news for you today, I don't think, so why don't we just kick straight into the puzzle. The rules are as follows. Normal Sudoku rules apply. Digits along an arrow must sum to the digit in that arrow's circle. So what that's telling us is that those three digits there, let's put 1, 2 and 3 in there. If you put 1, 2 and 3, they add up to 6, and that would be a legitimate way of filling in this circle and this arrow. Cells separated by a white dot must contain consecutive digits. So we've got 2 of those. So if that was a 1, this would be a 2. That's how that works. Just make sure the dots are consecutive. Not all possible dots are given. So that means it would be fine for this domino to contain consecutive digits, or this one. All we know is that these two dominoes definitely have consecutive digits in them. Digits in cages sum to the small clue in the top left corner of the cage. So you need to make sure those two cells add up to 14, etc. Cells that share the same position. Oh, okay, yeah. So we've got disjoint subsets today, which is it's my bête noire, frankly. I'm absolutely useless at solving puzzles with this constraint, but it normally leads to much hilarity on part of viewers. So cells that share the same position in 3x3 boxes may not contain the same digit. So, and there's an example here. It says if there is a 1 in the top left cell of box 1, so let's imagine this cell here was a 1. Now you cannot put 1 in the top left of any other 3x3 box in this puzzle. So obviously, I say obviously, so that means you couldn't have a 1 in any of these blue cells. Now obviously you could never put a 1 in those blue cells anyway, because normal Sudoku rules would rule that out. But the thing I find troubling is, you know, if I'm scanning this box, to realise that this cell cannot be a 1 because there's a 1 in the top left corner of the grid is unnatural to me. But this is what we are required to do. So one way of thinking about this rule set actually is to think about the blue squares there. These blue squares form a set of the digits 1 to 9. There must be 1, 1, 1, 2, 1, 3, etc. all the way through to 1, 9 in the blue cells. And then if we were to repeat that with, say, the middle cells in the boxes, those digits all have to be different. So they're obviously a complete set of the digits 1 to 9, etc. So for every individual position within a 3x3 box, this rule must apply. So do have a go at the puzzle. The way to play is to click the link under the video as usual. Now I get to play. Let's get cracking. And I'm going to start by noting that that cage is sort of a gimme. That's an 8, 9. It's the only way of getting to 17. That's the only way of getting to 16. Now we can also see that I think all of the arrows in this puzzle are 3 cells long, and they all seem to be 3 cells long in a manner. Yeah, they're all in a manner which means that they can't have repeated digits on their arrows. So that means that the minimum total we could put on any of these arrows would be 1, 2, and 3, which means each circle in this puzzle has to be at least equal to 6. And that is very good for this cell in particular. But look, there's loads of eliminations we can now do. We've got 8s and 9s removed from those two. We've got 7s and 9s removed from these two, and that seems to mean that this cell here has to just be a 6, which means this cell here is an 8, and we must put 1, 2, and 3 on the 6 arrow. We must put 7 on this circle. We're away here. We've got 1, 2, and 4 on this arrow, and there's some sort of sneaky Sudoku we can do here. We can ask where 1, 2, and 4 go in row 3 of the grid. They've got to go on that arrow now because they can't go in those cells. And that makes this circle equal to 7, which means that circle is not 7. Now, I was about to say it makes this circle not 7, but let us not forget the madness that exists within this puzzle, because this 7 is ruling out a 7 from any central position, so those are not 7s. Yeah, this works again. Let's just do that again. 1, 2, and 3... here have to find a home in column 7, and the only homes that are valid are going to be on that arrow because you can't put them down there. That makes that arrow add up to 6, which means we can remove 6 from these two. So these are they are different from one another. They are an 8-9 pair. Now, can we keep this going? This circle can't be 7 or 8 anymore. Now, what about this? What about this cage? Now, this cage, well, the way I saw this, I think there are a few ways of seeing this, but the way I saw it was there's obviously a 6 and an 8 in these 3 cells, which means that in box 1, we've got to put 6 and 8 into 2 of these 3 cells, which means there must be a 6 or an 8 in the 14 cage. And once there's a 6 or an 8 in the 14 cage, the other must also join it in order to add up to 14. Now, I'm probably not going to get a chair in mathematics for that, but it's still true. So that's a 6, 8. This square here is now a 9. And okay, so we have got 6, 7, 8, 9 around the Phistomefel ring. I'm just wondering about those 3 cells and whether or not I can pull the same trick by arguing that they are the same as those. And I think I can, because the only way that these 3 cells are not immediately these 3 cells is if one of these cells is in one of these cells, which would mean you'd have to put 6. So this would have to be a 1, 2, 6 arrow. But it can't be a 1, 2, 6 arrow, because the moment we make this arrow 1, 2, 6, that means we've got to put 1 and 2 on. Oh no, that could work. No, that could work, because this could be 1 and 2 and not add up to 9. Yeah, no, that's okay. Right, so I have to be careful. I can't just write this in and say it's here. Oh, bobbins. But I get a 6, 7 pair there. Because I've got 8 and 9 looking at 13 cage, so it can't be 4, 9 or 5, 8 anymore. Oh. Okay, so that's done it for me in a much more simple way. So now I can come back to this arrow and note that because it can't be 1, 2, 6 anymore, it must be 1, 3, 5 or 2, 3, 4. And none of those digits are appearing in this column yet. So whatever I put in those 3 cells there, oh, I don't like that. I don't like the orange against the arrow. Whatever I put in these 3 cells here now has to go on those 3 cells, which means that is a 9. Right. And that's absolutely beautiful, because now I know what these 3 cells are because of the white dot. Because the options left for the 9 here are either 135 or 234. Now the problem with 135 here is that these digits cannot be made to be consecutive with one another. That's beautiful. So that's got to be 234, and this has got to be 234. And now you can't put 2 and 4 on this domino, so there must be a 3 on this domino, so that's not a 3. So this is 2 or 4. 8 can just be placed by Sudoku in box number 7. So these squares have got to be a 1-5 pair. And this is where the madness is going to sort of manifest itself, isn't it? Because we're going to have to be judging whether or not 1 and 5 are appearing in any of these cells. Which they don't seem to be at the moment. But now, how do we do this then? 9 in box 1 has to go there by Sudoku, which means these 2 squares are 3 and 5. Let's check. We'll check the mad cells again. I don't think that's resolved. Oh dear. Okay, this is all ground to a bit of a halt, hasn't it? 6. Where does 6 go? It's very interesting sort of rotational logic here. We keep finding similar bits of logic affecting these arrows, but the 6 in box 9 now can't go on the 8 arrow, so it must go there. Yes, and yes, look at this. You've got the same thing. Those 3 cells have to find a home in box in row 7, so they're going to be the same as those, which makes this square. Oh, and we knew that because we knew they were a 9-8 pair, so I could have done that before, but this is sort of all proving itself. It almost feels like Phistomefel is being demonstrated to me by these weird positions of the arrows. So Phistomefel, of course, is the theory or theorem. I better get my mathematical terms right today, good grief. It's the theorem that tells us that those 16 cells around that ring, I can make these orange, so these orange cells are exactly identical to the 16 cells in the corner of any Sudoku puzzle. Now here, that seems to be very... I mean, it works for any Sudoku puzzle, but here you can see it's rather beautifully shown. You've got 1, 2, 4 here, 1, 2, 4. You've got 2, 3, 4 here, 2, 3, 4. Whatever we put on this, we know is the same as those. Whatever we put on this, we know is the same as those. So all we need to show now is that the corner digits in the orange cells are the same as the corner digits sort of in the purple. We've got a 6 here. So that corresponds to that 6. We've got a 9 here corresponding to that 9. We've got an 8 here corresponding to that 8. And we've got a 7 here which needs to correspond to that. And does by Sudoku. So yeah, there's sort of Phistomefel being demonstrated. 7's here, 7, 7. That square here, sorry, that square there has to be the 7 in box number 3. Sorry, now let me get rid of the colouring. That was just an excursion into Phistomefel land. And we've got a 4, 5 pair here. And I haven't looked at this yet. Now, is that disjointed some? Yes, it is. It can't be an 8. There's an 8 in the top left of that cell, so this is not 8. So it's 6, 7, or 9. Now, I bet it's not 6 or 7 for a mathematical reason, which is appropriate. 15, 16, yeah. This is beautiful. Right, okay. So, look at these 2 arrows. And let's think about the maths of this circle. Because this circle is represented algebraically by the sum of those 3 digits or the sum of those 3 digits. So if we sum those digits and sum those digits together, we know that we've got 2 lots of the circle. But the minimum value of those 5 cells, double counting this, is going to be, well, the triangular number for 5. We can make these a 1, 2, 3, 4, 5 quintuple at the least. So that's going to be 15. And then we have to double count this cell. So let's make that the smallest it can be and make that a 1. That's 16. So the absolute minimum value this circle is 16 divided by 2, which is 8, which we've just shown it can't be. So that is 9. And these must each add up to, therefore, 9. To state the blithering obvious, or the bleeding obvious, whatever it was that Basil Fawlty told Sybil was going to be his mastermind subject, or her mastermind subject. Now, so, okay, so 9 has to be in one of these. Now what do we do? Is this where it's going to get really tricky? We can... Yes, it is. This is where it's going to get tricky. Where do the 6 and the 7 go here? There is a 7 up there. It's so mad, this. You've got to be able to realise that this 7 sees that cell. So that can't be a 7, or there would be 2 7s in the top middle position of boxes. So that, I did not mean to do that. So this is 6, that's 7. Now, what's that done? I don't know. Yeah, look, it's the same here. There's an 8 here, which I think sees that cell. So that's got to be a 9. So that's an 8. So 8 is now in one of these 2 positions. I bet this is... Yes, this 8 sees that one. So the 8 goes there. I was thinking about where 8 went in this box, and I just realised 8 can no way go on a 3-cell 9 arrow. So 8 can't go there, can't go there. That's an 8. And that means 7 goes here. And that's because 7 also can't go on a 3-cell 9 arrow. So 7 can't go on an 8 arrow. So 7 is in one of those 2 cells. And I'm checking the... I don't know that that is resolved, actually. I think it'll be resolved by Sudoku from here. 9 here resolves the 9 in box 6. 7 by Sudoku goes there, look. That's just normal. 7 by Sudoku goes here. How many 7s have I got? 1, 2, 3, 4, 5. I've got 7 and just these to resolve. Okay, so what's the next best digit? 8, do you think? We've got 6 8s. Yes, I can get an 8 here. That's an 8. So 8 must be in one of those 2 cells. And again, I'm not sure whether that's going to get resolved or not, other than by maybe which of these is a 6. Okay, let's have a look at, do we think 9s or 6s? Let's have a look at 6s first. So 6s have to be in one of those 2. Yes, this 6 sees that one, so that's not 6. So this is 6. Oh. That's really beautiful. Okay, so where does 6 go in the middle box? And the answer at first blush is in one of those 2 positions, but it's definitely not here. Because if we put the 6 here, this cell has to contribute to both 9 sums. So you'd have to put 1 and 2 there and 1 and 2 here. Well, that's clearly not going to work. So this square here has got to be the 6. And now we know that those 2 squares have to be a 1, 2 pair. Now, we've done quite a lot of 6-age now. Yeah, look at this. Where does 6 go in this box? Now, it can't go on an 8 arrow. Well, for 2 reasons. So it's in one of those 2. But this one sees that one, so it's got to go here. So 6 is in one of those 2 cells, and it's not. Here we go. Look, it's not the top left because there's already a 6 in the top left. So that's a 6. That's a 6. That's an 8. That's an 8. And now 1, 2, 3, 4, 5, 6. We've done all the 6s. We've done all the 8s. And the big digit I've not looked at is 9. Now, can we do much with 9? I think 9 has to be in one of those two cells, and yes, I'm doing it a disservice. 9 here is seeing that cell, so 9 is there. That's 9, that's 9, that's 7, that's 7. So now I've got loads of 9s. I've got 4 9s looking at box 2. Whenever you have 4 of a number looking at a box, you can always fill that number in, providing you haven't made a mistake. All the 9s are now done. So now, what do we have to do? We've got to do Sudoku on the small digits. So let's have a quick fill-in of pencil marks. Those have got to be a 1-5 pair. It's probably going to be this arrow that's critical. I'm just trying to see if I can see anything else that's obvious. This white dot. 1, 2, yes, it's got to have a 2 on it, because we can't make this a 1-3 pair, so this square is not able to be 2. Not sure actually. 2, 3, 4, 5. I mean, I could pencil the whole of the bottom of the grid, but I'm not exactly sure, because I know literally nothing about 1s, 2s, 3s, 4s and 5s, other than these sort of dots. Oh, and this arrow. Yeah, let's check this arrow. So if this is a 1, this must be a 3-5 pair. And if this is a 2, this must be a 3-4 pair. So there is always there's always a 3 in one of those two cells now. So this cell in the centre is a 4 or a 5, which means it's going to be a 5, because you always get 5s in the middle of it. Well, I think it's proportionally likely to be a 5 if you were to take a sample of all cracking the cryptic puzzles we've ever solved. Oh. Okay, where does 3 go? In row 6? That's a sensible question. That's actually quite beautiful as well. This sort of naked 3, if we want to call it that, has been caused by this white dot. So that white dot stopped that being a 3 and actually led to this being a naked single. So that's a 3, that's a 1, that's a 2. So that's going to... Right, so this is a 5, this is a 1. Suddenly we may be away. Yeah, that's a 5 now by Sudoku. This is a 3, therefore this is not a 3. This is not a 5. And this 5 sees that cell, so that's 4, that's 5, that's 3. We get a 4-5 pair. The 1 here sees the 2, so this needs to have a 4 on it to make it add up to 9. That's a 5, this is a 1. So that's not 1, that's not, we don't know. Oh, that is 1, because it sees 2 and 4. 3, 5, is this resolved at the top? Probably in a way I can't see. That square's got to be a 3 or a 5, which is very annoying, because that doesn't actually disambiguate the 8. It could be 1, 3, 4 or 1, 2, 5 still. But it must have a 1 on it, mustn't it? So this one here tells us where that is. So this is the counterpart to this. We can think about these two cells having to add up to 7. So this is a 2 or a 4, which gives us a 2-4 pair in the column, and therefore presumably a 3-5 pair in the column, which gives us a 3-5 pair in the box. So that becomes a 2 or a 4, which we could have got another way, but never mind. Now, okay, I've got a bad feeling about this. This is going to be about disjoint subsets. No, don't be about disjoint subsets, please. Oh, it's going to be so difficult to spot whatever it is. Okay, come on, let me just think about this for a second or two or three. I can't see it quickly, that's for sure. What's maybe I don't know. Oh, look, 2, 3 and 4 there, so that's just a 2. Look, there are 8 digits already in that. So there we go, we can actually do those digits. Is that actually of it? That's probably not of any help unless it's affecting one of the disjoint cells somehow. But there could well be other rows and columns that are sort of replete with digits that I'm not spotting. So these have got to be 2, 3, 4, 5. That is not 4. That is not 5. Is this... yeah, this one is seeing that one, of course. So that's got to be... so there's now a 3, 5 pair in this row, which means that isn't a 2 or a 4. And... desperately trying to see whether that's hitting anything in the top right hand corner of boxes. I don't think it is. We know there's a 1 in one of those. Does the disjoint thing tell us which one it's in? It's not in the bottom, it's not in this one, look, because there's a 1 there. So the 1 is in one of those 2 cells, which means this is not a 1. 1, 2, 3. No. Okay. So what do we do to unravel this little enigma? We shall. Thing is, I'm sure there's going to be something fairly beautiful about it. So I don't want to quickly just try and force it. I'd rather try and spot something cute. So just give me a moment or two to try and spot whatever the cute thing is that's hidden in the puzzle. 1, 2, 3, and this is 2, 3, or 5 in the corner, and that does see that cell, look, by disjoint. So there's a 3, 5 pair now in this box, which means these have to be 1, 2, and 4. Which means that square has become a 3, I think. Which means that's a 5 and that's a 3. Which means that's a 5 and that's a 3. Wow, okay, and that's fixed this 8 arrow. So that 8 arrow is now 1, 3, 4, which means this is 1, 3, 4 by Sudoku, and that may be the thing we needed. Look, 2 and 5 go in here. Now, can we do the 1 and 4 by... how should we do this? Are we going to do it by disjoint? Probably. Is there a 4 in the middle of the bottom of a box somewhere? Not yet, but there might be one soon. Those squares have got to be a 1, 2 pair. And this 4 is seeing that one, so that's 4, that's 2, that's 2, that's 4, that's 4, that's 1, that's 1, that's 5, that's 5, that's 3, that's 2. So this is a 1, 4 pair. That 4 will deal with that. So that's 4, that's 1, that's 1, that's 2, that's 4, that's 5. Very pretty indeed. And a very happy birthday indeed to missing a few cards. We've had this puzzle recommended quite a few times over the last week or two, and I can see why. So I hope you all enjoyed it. Let us know in the comments. I do enjoy the comments, especially when they're kind. And we'll be back later with another edition of Cracking the Cryptic.